So, as a final part of Laplace transform, we'll be interested in characterization of our LTI systems using the Laplace transform. Right? Now you know that mm, in our time domain, LTI systems they are characterized using the convolution integral. Right? So if I have a system with an input x of t, it has an impulse response h of t, then I can say that the output of this system it is x of t convolved with h of t, right? Which is then equivalent to that integral x of t into h of t minus tau, h of tau d of tau, right? We had analyzed this in time domain. We had also computed few signals and yeah, and then computed their convolution, right? Now, if I apply Laplace transform on both sides here, so we don't need this integral here. If I apply Laplace, so it will be Laplace transform of the output signal and Laplace of this convolution. Now we already know that convolution it translates to multiplication in the S domain. So I can say y of s, assuming that y of s is a Laplace transform y of t, it will be equivalent to x of s multiplied by h of s. So x of s here is Laplace transform of input signal and h of s is the Laplace transform of the impulse response, and y of s is the Laplace transform of the output signal. So this becomes a defining relationship in the S domain. Alternatively, we sometimes express h of s as a ratio y by y of s divided by x of s. Now, when s is equivalent to j omega, that is when we are talking about Fourier transform. तो उस केस में your h of s it becomes h of j omega, and we simply say that it is the frequency response of the LTI system. Fine. But in a broader context, when you talk about Laplace transform where s is equivalent to some real part and some plus some imaginary part, then alternately this h of s it is referred to as system function. Yeah, sometimes some text they refer to this as a transfer function. Fine. And this system function or this transfer function can then be used to characterize an LTI system. If you remember when we did the time domain, when we did the convolution integral, then we expressed the system properties in terms of h of t, the impulse response. And यहाँ पे we will be trying to express the same properties in terms of this system function or the transfer function. Right? So let's start with one such property, that was a property of causality, and let's see how we can express this property for an LTI system in the S domain. Now, if you remember that for a causal LTI system, the impulse response h of t was 0 for t less than 0. This is how we established the condition of causality using the impulse response. Fine. So it means I have a signal h of t which is equivalent to 0 for t less than 0. In other words, I can say h of t is a right-sided signal. Remember the video on properties of ROC? So वहाँ पे I had explained this, what a right-sided signal is. I typically gave an example of unit step function u of t. So from t is equal to minus infinity to t is equal to 0, it has a value of 0, and then from t is equal to 0, it has some finite value. Right? Now, since h of t is equal to 0 for t less than 0 for a causal system, it means that the associated ROC with the system function of a causal system is right half plane, या you can say जो हमारा उस time properties में define किया था, that it lies right to the rightmost plane. So I can say, not plane, pole. System is a right half plane to the right of the rightmost pole. And this now becomes the definition of causality in terms of the system. So I can say that for a system, let me put it out here, the condition for causality for a system with rational transfer, a system function, whatever you want to call it, causality of the system is equivalent to the ROC, region of convergence, being the right half of a right half plane to the right of the rightmost pole. Right? Now this becomes the definition of a causal system. So we started with the definition of causality for a general system, that it is a that causal system is a system which only depends upon present and past values. Then we redefined it for an LTI system in terms of impulse response, that its impulse response should be 0 for t less than 0. We have again not modified it, we have alternately represented it in terms of system function. Jahan pe, now this is a kind of a graphical approach, because region of convergence, it's actually a plot, a region in the S plane. Right? So when you have a look at the region of convergence of a particular system, the associated system function, you can comment on the causality of such a system, which implies that if the region of convergence is to the right of the rightmost pole, then your system is causal. Okay. Now, alternately, it means that if a system is anti-causal, if we go by the definition, अगर आपका anti-causal system है, so for an anti-causal system, it doesn't satisfy this. Means h of t is not equivalent to 0 for t less than 0. Fine. Then you can say that in terms of ROC, if your system function is a rational system function, then if the ROC is to the left of the leftmost pole, we'll do an example shortly, उस time पे ये clear हो जाएगा, तो then the system is anti-causal. Right? So just by having a look at the region of convergence, that's why in the earlier videos I told you that when Laplace transform is concerned, one is its algebraic expression. Your algebraic expression is not that important, but what is important is the region of convergence. That how does this region of convergence look in the S-plane, and that will tell you about the property of the system. So we are defining causality here in terms of that ROC. So that if ROC is the right half of the rightmost pole, then your system is going to be causal. In case it is the left half, yeah, it lies to the left of the half of the pole, then it will not be causal, it may be anti-causal. Okay. Similarly, we had a second property, that was the property of the stability. And again, if you remember in terms of the convolution integral, in terms of the impulse response, this was the condition for stability, that your impulse response, it should be absolutely summable. That is the integral of h of t, it should be less than infinity. Fine. Now, if this is true, it means Fourier transform will exist. Just try to understand this point. Because one of the foremost conditions of Fourier transform is कि जिस function का Fourier transform निकालते हैं, it should be absolutely integrable. It should converge. Right? Now here the function under consideration is h of t. Now if the system is stable, it automatically means that h of t is absolutely integrable, which means इसका Fourier transform, it will be defined. It will converge. Right? Now we have already established a relationship between the Fourier transform and the Laplace transform, and we have seen that Fourier transform of any signal is actually the Laplace transform computed over evaluated along the j omega axis. Right? Because if you remember, of s computed over s is equivalent to j omega is actually the Fourier transform. Okay. So stability के लिए for an LTS system, its impulse response should be absolutely integrable. Now in terms of system function, it means you can define the Fourier transform of this impulse response because it is absolutely integrable. Then Fourier transform is related to Laplace transform in the sense that Fourier transform is actually the Laplace transform evaluated along the j omega axis. Right? Now this means in terms of ROC, I will have this particular condition for stability, that is an LTI system is stable, and stability is still the same, bounded input, bounded output. This is the concept of stability that we have been discussing. So it is Bibo stable if and only if the ROC of its system function h of s, it includes the j omega axis. Okay. Again we'll be doing an example तो उससे clear होगा. Now these are the definitions for our stability. We started with a simple description of a system जहाँ पे Bibo stable was defined on the basis of the bounded inputness and boundedness of the output. You gave a bounded input to a system. If its output is also bounded, we simply set it as Bibo stable. Then we moved on to LTI system wherein we characterize the system using the impulse response. तो वहाँ पे जो हमारा condition बन जाता था stability का, it was this, that the impulse response should be absolutely integrable. Now we are defining stability in terms of the ROC. That is, an LTI system is stable if the ROC of its system function, it includes the j omega axis. Right? Now we'll do a single example on this, wherein I am given a system function h of s. It is a rational system function. This is my system function. And the question is that what will be the ROC if I want this system to be causal? Right? And second, what will be the ROC if I want this system to be stable? And third, what will be the ROC if system is non-causal and unstable? So to solve this, we first plot the system function. Fine. So I have a plot here. Fine. So this will be my real axis. This is the imaginary axis. Then I have 1 0 0 numerator equate करिए 0 से, so 0 will be at s is equal to 1. So let this be the point. यहाँ पे मेरा 0 है. Yeah, just to distinguish it, let us use this is the 0. And I have poles at s is equal to -1 and s is equal to 2. So I have a pole here at 2 and at -1. Fine. So let me just, so this is -1, this is 1, and this right here is 2. Okay, this is my pole 0 plot. Okay, now पहला केस, पहले केस में he wants the system to be causal. Fine. Now causality का जो definition है in terms of ROC is that the associated, the ROC of the associated system function, it should be the right half plane to the right of the rightmost pole. Now rightmost pole is this, so if I draw an axis through this, let me like this, ठीक है, और जो आपका फिर ROC होगा to maintain this causality, it will be to the right of this. So if you have system function जिसका region of convergence is like this, then this will correspond to a causal system. So this is my causal system for this particular what you call system function. Okay. Then the second case, if now I want this system to be stable, again I will just quickly plot it. This is sigma, this is j omega. I have a 0 at 1, then I have two poles, one here and the other one at -1. Right? Now comes the condition for stability. Stability के लिए we have to ensure that your ROC should include this axis, the j omega axis. It should be a part of your region of convergence. साथ ही में if you, which means, let me just like this. अब चूंकि आपका j omega axis should be a part of ROC. दूसरा हमारा first property ROC का, it cannot include poles. So it obviously means for stability of the same system, your region of convergence should be this strip from here to here. We cannot go beyond this, because if we go beyond this limit, then our poles will be a part of our region of convergence, which is not allowed. Zeros can be a part because 0 is a finite value, so it can very well be a part of your region of convergence, but pole cannot be a part of region of convergence. So this will be for a stable system. Then finally we have the system, if the system is not causal and it's an unstable system. Okay, so if I copy the same thing, and now I have to see what will be the ROC look like. First thing is the system is non-causal. So जो आपका ROC होगा, it should be to the left of the leftmost plane. Then the system is also unstable. Fine. So it means it should not include the j omega axis. Now इस system के साथ only one combination fits that description, which is this. That if we will have ROC to the left of the leftmost point. So with this ROC, it ensures both the things. First, j omega is not a part of the region of convergence, so the system is unstable. Second, the region of convergence is the left plane of the leftmost pole, so it is non-causal. So this particular is for non-causal and unstable. Okay. Now if I want, okay, let me just add one more thing here. If I want the system to be stable and causal, is this possible with this arrangement? So I want my system to be causal as well as stable. अब causality के लिए it should be to the right of the rightmost plane. So if I draw the line here, then for causality it will be determined by this. Yeah, so causality के लिए it should be like this, to the right half of the rightmost. And stability के लिए it should include the j omega axis, right? Which means for stability it should be something like this. As you can see, there is no intersection. Again, this is isolated, this is isolated. So obviously with this system description for this h of s, we cannot have a system, we cannot design a system which is both stable as well as causal. Okay? Now this is an interesting thing here. अगर आप देखें तीनों cases में, whether we are discussing causality, stability and this thing, you have the same system function. System function में कोई change नहीं आ रहा है. But how, yeah, what is the region of convergence associated with this system function, that will define causality and stability. So if I have the system function like this and this is my associated ROC, then I will be having a causal system. If I have a system function this and this is the associated ROC, my system will be stable. Similarly, if I have a h of s this system function and this is the associated ROC, then it will be unstable and non-causal. So this is again the importance of the region of convergence, क्योंकि तीनों cases में आपका जो system function h of s, mathematically it still is the same, right? But your ROC will define, the nature of your ROC will define the exact properties of your system, right? So this was all about the characterization of an LTI system in Laplace transform, specifically in terms of the region of convergence, right? So this is all about the Laplace transform. Isme there is one topic, inverse Laplace transform, but that is just a mathematical portion. वैसे भी we are not having offline examination, so you can take that as an assignment. या आपने mathematics में पढ़ा होगा, because it involves use of partial fractions. So I hope Laplace is also a part of your mathematics. Since that doesn't have that much of a physical significance, so we will skip that part, right? So this was all about Laplace transform. And next time we will do the similar kind of analysis for the discrete time case, and usme we'll be doing the analysis through the Z transform. Then again, I would like you people to compare. जैसे मैंने कहा था कि whenever you learn a new transform technique, compare it with the previous one. यहाँ पे Laplace transform, we compared it with the Fourier transform. In fact, in the first video only, we try to establish a relationship between Fourier transform and the Laplace transform. Similarly, when we do the Z transform, try to compare it with the discrete Fourier transform.